Okay, so to go on to the multiple choice, the function g is continuous at all x except at x equals 4. If the limit as x approaches 4 is equal to infinity, which of the following statements about g must be true? G of 4 is equal to infinity? No. The line x equals 4 is a horizontal asymptote? Nah, that's terrible. Nope, can't be horizontal, it can't be that right there. It's a vertical asymptote at x equals 4. Yep. Sorry, no, y equals, no. Vertical asymptote at x equals 4. Yes, yep, I was right. Can't be a vertical asymptote at y equals 4. That doesn't make any sense. For 2, the function g is defined given here. Oh, great. Got some absolute value stuff happening here. At what values of x does the graph of g have a vertical asymptote? So we would have to. I'm not going to check here. So this shouldn't be any vertical asymptotes right here. We've talked about how they're like, well, if we ignore this right here, not that we really can because it's part of the graph, but there shouldn't be a problem with vertical asymptotes with this expression right here. There can be vertical asymptotes due to this denominator right here. So at x equals 0, I would definitely say that there has to be vertical asymptotes. And then, well, one thing that you guys should be aware is that natural log functions have asymptotes. So natural log functions, or log functions, I guess I should say in general, if you guys remember graphing these right here, they have vertical asymptotes kind of at the beginning of their domain. So the parent function of the natural log function will look like this right here. And the domain of the natural log of x is such that it has to be greater than or equal to 0, and it approaches negative infinity down here. There's a vertical asymptote for logarithmic functions. So logarithmic functions have asymptotes, vertical asymptotes, always, and it's where they begin. And so that's going to be where they, you have to check where they begin. And how do you know where they begin? It's whenever what's inside of them is 0. So for example, this is the natural log of x. Its domain starts at x equals 0 because natural logs, you can't put a negative number inside them. So if you had something like the natural log of x plus 2, well, where's the beginning of the domain of the natural log of x plus 2? It's at x equals negative 2, since this is the lowest x value I can plug in without it being 0 or negative. What's the lowest x value for the natural log of x minus 2? That's going to be at positive 2. That's the lowest x value you can plug in here to be 0 and not negative. So it can't include 2 either, unlike a square root. It can't include 2. That's why there's that vertical asymptote. And so keeping that in mind, x plus 5 over x squared has to be greater than 0. But this doesn't matter right here. You basically just want to check for the numerator. So when does x plus 5 equal 0? And that's going to be when x is negative 5. And so there should be 2 vertical asymptotes. That's going to be at 0 and at negative 5. So I'm going to say it's going to be C. Okay. So kind of going back to your algebra, knowing your domains of functions is always going to be beneficial when you're doing problems in calculus. The function f, the values of f of a function f can be made arbitrarily large, so like positive and negative infinity, by taking x sufficiently close to 1, but not equal to 1. Which of the following statements must be true? So values of f of x can be made arbitrarily large by taking x sufficiently close to 1. So x is approaching 1, but then the values of the functions, so the limit as x approaches 1, the values of the function are going to be made arbitrarily large. So that's going to be positive infinity, so it's going to be c. Let f be the function defined here. Which of the following is a horizontal asymptote of the graph of f? So I'm looking at whenever you're thinking about horizontal asymptotes, you have to be thinking about large values of x, as x is approaching positive or negative infinity, positive or negative large values of x. And what happens to the values of these functions at these values? You're thinking about the overall magnitude. So at very large values of x, 5 and 1 are insignificant. 5 and 1 are insignificant at large values of x. Okay, they're not going to have any sort of effect on the actual values of the parts that have like a x in them. So I'm going to ignore these since I'm thinking about this function at large values of x. And so let's just think about 2 to the x over e to the x. And let's think about the limit as x approaches, let's say, positive infinity. At positive infinity, well, I can see e is equal to something larger than 2. So so this exponential has a larger base than this exponential, which means at very large values of x, this is going to grow faster than 2 to the x. It has a larger magnitude. And so whenever that happens, because the denominator is growing faster than the numerator, eventually it's going to be equal to 0. And you can say the same thing. No, I think that's about it right there. We can say that we can... no, I think that's all that we want to do there. I think x equals 0. That's our only option as far as the choices here. Y equals 0. So it can't be 2 over e or 1. So that should be it right there. Yeah. So again, when you're evaluating for horizontal asymptotes, think about the limit as x approaches positive, negative infinity. So, well, let's do the limit as x approaches negative infinity of 2 to the x over e to the x. So what's happening to the graph at negative infinity? Because we also need to check that right there. Well, if you think about very negative values of x for here and here, if you use the negative exponent rule, these would flip. So then you can say that this would be, I think you could probably say that would be equal to the limit as x approaches positive infinity of e to the x over 2 to the x. And then, well, this right here, since the e is in the numerator, it's going to grow faster than here, so that's just going to be equal to positive infinity. So this, so one side of the graph, the left side of the graph is going to be at positive infinity, while the right side of the graph is going to be at 0. So it's still only one horizontal asymptote. Okay. Let f be the function defined here for which of the following is a horizontal asymptote. Okay, now this one, kind of the same idea. We're thinking about very large or very negative. However, this is a rational function. So whenever I'm thinking about very large numbers, I just have to think about the highest degree of both of these parts right here, the numerator and the denominator. So take these terms, because at positive and negative infinity, the other terms aren't going to have any sort of serious effect on the values of the function. And so I don't really need those terms. So if I think about negative 2x squared over 3x squared, well, since these powers are the same, again, those are eventually going to cancel out at very large values. So the ratio will remain whenever you're evaluating the limit. So the limit as x approaches, I'm going to say positive or negative infinity, of an expression such as this right here. The ratio is the only thing that's going to remain, the ratio of the leading coefficients, so negative 2/3. So that's going to be the placement of the horizontal asymptote. And if you guys need to graph these, just to kind of give an idea, please do so.